we continue with the same structural member for this example, but now we consider 7 random variables in place of 2 as we did before, and we are going to solve this using Monte Carlo simulations. As you see, there is dependence among these 7 random variables, which we're going to describe shortly. So let us go through them step by step. We have the same 3 limit states as we did before. Some of the numbers, some of the descriptions will be different from problem H1, and we are going to use the SI system for units. So the load variables are P and W. P is Gumbel, W is normal. However, their means are given in terms of kilonewton and kilonewton per meter, and they are dependent. So we have partial information about their dependence given in terms of their correlation coefficient, which is 0.2. The strength variables, there are 2 of them, Y and E, the yield strength and the Young's modulus. Now they are both random variables, they are both log normal, and they are mutually independent, because there is no reason to have yield and stiffness have any dependence between them. We don't observe that usually. The geometric variables, the span is now 3 meters, which is non-random. Now let us now use some real sections and values of these geometric properties through a design. So let's say we have gone through the design, and it turns out that ISWB wide flange beam 250 is the appropriate beam selected for this load, and the geometric properties along with the randomness is R. So the area resisting shear has a nominal value of 16.8 square centimeters. So let's say it's a log normal random variable with mean 1.05 times the nominal, which means the bias factor is 1.05, and a COV of only 5%. Likewise, the moment of inertia, which is almost 6,000 centimeters to the power 4, is also considered to be log normal, which is a common assumption, with again a bias of 1.05 and a small COV of 5%. The plastic section modulus has a nominal value of 475 cubic centimeters, and the bias is 1.1 here, and the COV is a little larger at 7%. So these define the geometric random variables, but now they are mutually dependent. So again, we have partial information about their dependence. It is the correlation coefficient between each pair is 0.2, and then the failure modes. So after defining these 7 random variables, the failure modes, there are 3 of them, as we have already discussed in the previous example: flexural failure, shear failure, and deflection failure. And these are the forms of the limit state equations. You have the applied load or the applied moment and the moment capacity. So it's a capacity demand type formulation. So we have for bending, we have for shear, and we have for deflection. This time the limit on deflection is span over 100. So putting all of this together, now we could actually write Monte Carlo code and go through and take it to solution. So let's go through the steps of the Matlab program that I have written for this purpose. We first define all the random variable parameters. So we define the mean of P, the COV of P, and because it's Gumbel's, we obtain the corresponding U and alpha values. We define the mean and COV of W, which is normal. Then we define the correlation matrix between P and W, and again, to save space, I have written it out in one line. So rho of PW is 0.2, and the correlation matrix is 1 rho PW semicolon rho PW 1. So that's a 2 by 2 matrix. And then because I'll need this during simulations, the Cholesky factor of the correlation matrix. And I would like to have the lower triangular form, so that's why I take the transpose of that, because somehow Matlab gives the upper triangular form. And then because I'm going to use these later, I initialize the vector y for PW 1 and 2. And I'm going to need that because I'm going to combine two independent normals through this sort of Cholesky factor. Then I go to the geometric values. So I'm sorry, I go to the strength values. So the yield strength and the Young's modulus, Y and E, they are independent. And I obtain their corresponding log normal parameters. And we need to remember that they are in different units. So one is in megapascal, one is in gigapascal. So once we put all of them together in the Monte Carlo loop, we need to make sure that we are respectful of the units. Then we look at the geometric quantities. So I have the I, the sectional moment of inertia, which is again log normal. So I obtain those parameters. Sz, which is also log normal, so I obtain their parameters, and the area shear, which again log normal, and I obtain its parameters. So I have defined them, and it so happens they're all in terms of centimeters, centimeter to the power 4, 3, and 2 respectively. But then I need to incorporate their dependence. So I have been given the correlation coefficient between each pair, so, and which happens to be 0.2 for each of them. So I need to define the 3 by 3 correlation matrix, which you see in the first line there. It's 1 rho SI, rho SA, then next line rho SI 1 rho AI, and the last line is rho SA, rho AI, and A. So these are the 3 by 3 correlation matrix between SZ, I, and area shear. And like I did for the loads, I need the lower Cholesky factor, which is what you see in the second line, and I initialize the vector that I will need for the Monte Carlo simulation. Next, the length is 3, which is non-random, and it's in meters, so we have to be mindful about all these different units. Next, we are ready to start the Monte Carlo loop, so I initialize the counters. The count any is any failure, count flexure for flexural failure, count shear for shear failure, and count deflection for deflection failure. And I'm going to need some of these moments of the estimate, so I initialize some I flexure and some square I flexure as well. And I also need to define the number of Monte Carlo trials. Here I seem to have about 100 million simulations. It's, I think, the last case that I studied. Now we enter the Monte Carlo loop. I generate the independent Y's and E's, so that's simple, and I need to make sure that I'm being consistent with the units. So that's what you see in these two lines, rand n being the standard normal random deviate. Then I need to generate the dependent SZI and A shear, and for that I generate 3 independent normals, ZZ1, ZZ2, and ZZ3, and then I obtain the intermediate y using the linear combination of the ZZs. So that's where that lower Cholesky factor comes in. And then from each of the y's, I obtain a Z, I, and A shear through the log normal transformation. So that gives me the three quantities, and there I have also been mindful of the units. Then the loads are generated in a similar manner. I first generate two independent standard normals, Z1 and Z2, and then combine them with the lower Cholesky factor, and then transform each of the y's to P and W respectively. I'm again mindful of the units. Then I introduce three flags because I want to keep track of how many of the limit states, which of the limit states have been violated, or which of the limit states are negative. So the first one is the bending limit state. So if the bending capacity is less than the bending demand, I increase the flexure failure count by 1, and I set the flag 1 up. And then the shear limit state, similarly, if shear capacity is less than shear load, then I increase the shear count by 1, and I set the flag 2 up. And finally, for the deflection limit state, similarly. And this lets me keep track of both the whole system failure as well as the individual failure modes. If any of the flags are up, I add the total system failure by 1. So that's count any is incremented by the max of the flags. In the next slide, we are ready to output all the results. So the total failure probability is the count divided by the number of simulations. I find the equivalent beta through the normal inverse function. I also find the estimated COV through the estimated total PF. And then I output the results on the screen. I do the similar thing now for each failure mode. So the flexural failure count gives me the flexural beta and the coefficient of variation of the estimate, and I print the results on the screen. Do it the same thing for shear failure, and finally for deflection failure. And when we go to the next slide, we will study the results. Let's take a look at these results. We have these 7 random variables as I described, 3 limit states. So on the left set of columns in light green background, we have the flexural limit state. Next 3 sets in light pink background is the shear, and the light blue background, the deflection. And the very last set of columns is the system limit state. On the very left column, I have the number of Monte Carlo simulations. So if I have about 10 to the power 5 simulations, then let's see the results. The estimated flexural beta is 3.63. However, the COV of the estimate is rather large. It's more than 25%. In shear, the limit state is so far back in the standard normal space, if we may use that analogy, no failure is detected. So the failure probability is probably several orders less than 10 to the minus 5. The deflection limit state has a lesser failure probability than flexure, which makes sense. The equivalent beta is about 3.69. The uncertainty is quite large. It's about 30%. For the entire system, which is the union of these 3 individual failure modes, the estimated beta is 3.53, and the uncertainty is about 21%. We should have a little lower uncertainty, lower COV of these estimates. So let's now increase the number of simulations to 1 million. You see the beta is in those same ballpark figures. So for flexure it's 3.57, for deflection 3.67, for shear still no failure observed, and for the system it's 3.47. The uncertainty is all less than 10%, so we could actually have stopped here. But let's go on just because we can. So 10 million and then 100 million simulations, and the uncertainty comes down to less than 1%. So clearly the system beta is 3.45, the flexure beta is 3.55, and the deflection beta is 3.7, and no shear failure has been observed, so we really do not have any estimate there. If we really wanted, we could do an FORM analysis of the shear limit state and obtain an estimate of the beta. If one is interested, such an exercise could be undertaken.